We'll be doing Fischer projections today. We'll get into that. Fischer projection is part of the lab report for the bromination lab. Because we're just now doing that, and instead of having that report due tomorrow and Friday, we'll say the report's due Monday here in class. Bromination report due Monday in class. Any questions about stereochemistry before we get going? Polarimetry of naproxen this week, pre-lab downstairs. We'll also cover this portion here, B, optical activity of enantiomers and enantiomeric mixtures. We'll cover that during the pre-lab, that portion there. And that is lecture material. Okay? We'll do that then. The lab is not that long. We got time to do that there. As we know, enantiomers have identical physical properties because they have the same sort of configuration of the groups there. It's just inverted or mirror imaged. But it's the same orientation of the groups, so it's the same density, same viscosity, same boiling point. Basically the same molecule, but it ain't. We've got to understand that. Just like these ain't the same hand. Now, for humans, one hand can do something differently than the other because we're just prone to be right-handed or prone to be left-handed. But now, enantiomers do different that they rotate plane polarized light one direction or the other. This is an interesting quirk. The history on the back page sort of gets at how this was discovered in the early 1800s. Starting with something like compounds like turpentine, natural compounds that were shown to rotate the light one way or the other. So that's the optical activity. Okay, here we go. Optical rotation of individual enantiomers of 2-butanol. Okay, do we see a chiral carbon? What's a chiral carbon? What does it do? Chiral carbon is a site of asymmetry. Okay? Chiral carbon, there is no symmetry. Asymmetry meaning no symmetry. No symmetry there. But if you have one place of no symmetry, it's going to ruin the symmetry for the whole molecule, and thus the whole molecule will not have any symmetry. And the whole molecule does not have any symmetry. What does that mean about the mirror image? Yeah, the mirror image would be different. So a molecule that does not have any symmetry is, the mirror image is different. It thus has an enantiomer, mirror image is different. We call that chirality. We call the molecule chiral, because the mirror image is different. Chiral coming from, I believe, Greek for hand. It's just like hand. You know, a long time ago, your hands were mirror images that were different. Again, such terminology is in the history there on the back page. We got a chiral carbon here. How do you recognize them? Tetrahedral carbon with 4 different things attached. That's one right there. We've got OH, an ethyl, a methyl, and an H. These groups are different. That's an ethyl, that's a methyl. Everybody agree that's different? So sometimes you guys don't think that's different. I don't know why. I think because they're both carbon groups. But they're not the same. That's an ethyl, that's a methyl, so they're different. Carbon with 4 different things, it's chiral. That is, you can have 2 different ways to orient the groups around that carbon. Yes, 2 ways. There's only 2 ways. We can thus show, we know that's tetrahedral. That's not shown as tetrahedral. Let's show this more precisely. We can show boom, boom, boom. Here we go, right here. 2 in the plane, 1 forward. And 1 back. What's going back there? I'm drawing hydrogen. I'm not going to draw it in. Okay? We can draw this another way. Boom, boom, boom. we can put the OH instead back. Yeah, we can do that, right? Okay, what's the relationship between the two compounds on the board? I heard stereoisomers and enantiomers. How do you know they're enantiomers? Or are they the same? Are they mirror images? Let's start with that. Are those mirror images? Not superimposable. These are all reasonable ways to answer it. Are these mirror images? Who says they're mirror images? Who says they're not mirror images? Okay, why not mirror image?
If you're looking at it, they would be looking at each other from the front. You'll have one OH facing to the right and the other OH facing to the left.
Actual also would be on the other side.
No, if they're mirrored.
All right, let's talk about mirror images. What if I do draw this like this instead?
That's the same thing.
Consider this one. Is that the mirror image of this?
Yes.
Yes.
Far right is the mirror image of this? Everybody agree?
Yes.
Yes. The one on the far right is the mirror image of this. Yes. But so is that, because these are the same. Is that what you were trying to say? Yeah. Those two over there are the same. Okay? What I did on the board is kind of like this. Are these mirror images? Right and left hand mirror images? Okay, let me ask you again. Are these mirror images? Sure they are. They're right and left hand. Right and left hand are mirror images. I just didn't show you them mirroring, but they are mirror images. That's what we're doing here. Okay, the way to do this is there's two different configurations. There's R and S. If we do R and S, we can just know what we got here. What is R and S here? Oxygen is 1. What's 2? Carbon or carbon? Okay, you should be doing this with your EZ nomenclature. How do you do it? Both are carbons. How do you decide?
What are they bonded to?
What it's bonded to? What is this carbon bonded to?
2H.
H, H, H. You list them here, but high priority first. What is this carbon bonded to? Carbon, H, H. Carbon, H, H. Look at the first thing. Which is high priority, H or C?
C.
C. Game over. You don't have to go any further. This is high priority. Basically, with carbon chains, the longer the chain, the higher the priority it is. Because okay, that's pretty simple. That's 2. This is 3. What's 4? I'm drawing H going back. Okay, with the low priority group in the back, what is this? R. All right. Let's do this one real quick. 1, 2, 3. Low priority group in the back. What is it? S. The mirror image of R is S. Did I say that loud enough? What's the mirror image of my right hand? The left hand. The other one. Mirror image of R is S. Okay, so what is this one?
Yes.
Well, we can look at it in a number of ways, but how about if we just do R and S? What's 1? 1, 2, 3. Is that right? High priority group is where? Coming forward. What do we do if it's coming forward? Your book's going to tell you to do something. I don't know. This is what I tell you to do. Is if the high priority group is going forward, you just look at your numbers, clockwise or counter here?
Clockwise.
Clockwise. But the low priority group is coming forward. You just reverse it. And so you make it counterclockwise. So this is what? S. Same as that over there. It's the same thing. I told you there was the same thing. Yeah, at least they're the same compound, right? These are all stereoisomers. They all are everything on the board. 2-butanol. This nomenclature you're learning organic. 2 of alcohols. It's a butane with an alcohol, so it becomes a butanol, and the 2 is where the OH is at. terms of nomenclature, the N would be 1, 2. OH is at the 2. Are all these 2-butanol? Yes, they all are. The one on the right, the one carbon is on the right to make the group at the 2. These are all 2-butanol. Stereoisomers all have the same name, they just differ by some stereochemical descriptor. This is S2-butanol. So is that. What is this? R2-butanol. Yes. Okay, so we introduced how to determine R and S when the low priority group is coming forward. You just reverse it. We also introduced the idea, I haven't clarified it though. To show the enantiomer, you can draw it as a mirror, the way we've done it last time. But that's not how we typically do it. It's more common when you want to show the enantiomer to just switch your projection. Keep the backbone the same. Okay? I still have the same backbone, I just switch the projection. That will give you the other configuration. If it's chiral, that will switch you from R to S or vice versa. Just switch it from bold to dash or vice versa. So from now on, I will never draw things like this and actually say, hey, look, it's a mirror image. I'll draw it like this, and we know that it's a mirror image. Unless we have multiple chiral carbons or something. Questions about this? Yes?
So is it also better to draw it like the first way? Because in the second way, like, it still looks like the low part is coming forward, which makes it seem like it's odd.
On the far right?
Yes.
No, the low priority group is going back on the far right.
Oh, sorry, but back on that and also the third one.
Well, in terms of R and S, that should be easy for any of them. This one's R, the far right is S. The only thing is, the middle one, the low priority group is coming forward, so that one you have to reverse. So you get S for that, but then you see that both of these are what's the name of this? It's the same exact name, all right? It's the same compound. So, okay, but what do we need to look at? Optical activity. For S, it's positive 13.5. So for this one, alpha, rotation, but when it's in brackets, it's specific rotation. That's when it's been normalized. You'll be doing that in lab this week. Equals 13.5 degrees. The enantiomer rotates equal and opposite, so what is the enantiomer specific rotation? Negative 13.5 degrees, equal and opposite, but I told you that there. Since this rotates negative, we can call this something else as well. Negative, is that D or L? L, LIVO. Yes. We could also call this, you write somewhere, I'm writing on top of this. We could call this L, that's a little L. L, sometimes these in the front are put in parentheses, sometimes not. For some reason, I feel like this needs parentheses. L2-butanol. And this would be called what? D2-butanol. You might also call this negative 2-butanol because it's a negative rotation. You might call this positive 2-butanol. This is basically the same thing, both depending on the rotation. In order to use this nomenclature, you have to know how it rotates. You're only going to know that if you determine it or if somebody gives you the information. You can't look at a structure and tell how it's going to rotate. But you can look at a structure and determine R and S. Now, importantly, please don't think that R is always L or that S is always D. It's not. They have no relation to each other. Sometimes R may be D. Structure does not go with rotation. It's actually very random, and it's kind of quirky. Okay? For the example we did here. All right, now down below, in pre-lab, we'll do some calculations with this using this number here, 13.5 for that one. But that specific rotation becomes a physical constant for that compound and the two enantiomers there. Because chiral compounds are optically active. They rotate pp light in equal and opposite directions. Okay, identify chiral carbons in the following compounds. You guys got everything I just talked about here? Boom, good to go? Probably not. Could I go through that 5 or 10 more times? Did it help you? Go through it again? That's what the video's for. Okay. Chiral carbons. Any chiral carbons here? No. I mean, do you see tetrahedral carbon with 4 different things attached? The one thing I want to point out here is rings. Look at this carbon here, which seems to have possibly 4. I mean, these only have 2 H's, so 2 H's are the same, so that's not 4 different things. There's only 1 H here, chlorine. Are these 2 groups different? No, because if you start here and come this way, CH2, CH2, same. This is the same. Right? Not chiral. I don't want to do that, that means it's chiral. If I had a model of that, I'd be able to cut right through it. Basically, right here is your plane of symmetry. Bam. Half on one side, half on the other is the exact same thing. We'll do more of that later. But this is finding chiral carbons helps you then advance in your considerations of everything. How about over here? I put in a double bond. Chiral carbon? Anywhere? Is that chiral? What's the geometry of that carbon? Say the second word louder.
Planar.
Planar. A planar carbon or atom is not, well, not chiral because it's symmetrical. Something with a plane, you can slice right through that plane. It's like this paper. Here's the plane. I can slice right through. Now I have to maybe go to the nanoscale, but I can slice right through this plane and have half the paper on one side, half the other, assuming nothing's written over here and over here. I mean, an atom ain't going to have like words on one side and no words on the other. But now, it might be practically for us impossible to slice right through this plane. A piece of bread is thicker, we could slice right through it and make 2 pieces of bread. Well, you could too here. I just have to have a atomic scale slicer. Okay. Something with a plane is got a plane of symmetry. The plane is the plane of symmetry. It ain't a tetrahedral carbon, because tetrahedral either. Chiral carbons are tetrahedral carbons. They have 3D nature, and that helps lead to the asymmetry. There's no chiral carbon here. The plane of symmetry here is the plane of the board. Because that carbon is in the plane here. And I can slice right through half the carbon, right through here. All right, there's no chiral carbon here. This one has a chiral carbon, yeah? Everybody see it? Because if you go this way around the ring, that's different from coming this way around the ring. Everybody agree? With the lower root, you encounter a double bond. That one's chiral. And thus you can show 2 enantiomers. Just like we did above with the compound above. Okay? You should do that on your own. Okay. Basically, we're getting in what types of questions may you see here, how to work with this stuff. Here's another type of question. Which compound below gives a chiral product when hydrobrominated with HBr? Anybody get this? The third one? Anybody else get this one? I should say, did anybody else get an answer? I'll have to look at it. I'm not sure if it's what it is. Anybody else get an answer? So how did you approach this?
It's reduced electives for film with the tertiary one, and then it's chiral, because it doesn't have 4 different things attached.
All right. I would hope that you maybe would show the hydrobromination product for each one. Step 1, done. Then go back and look at them and say, okay, of my 4 products I showed, which one is chiral? And the question then becomes, first, can you show an HBr addition product? Second, can you recognize a chiral compound? Then we can say, will the product have RS configuration? Did you address that?
I don't, that's not the
Okay. Questions about that question? Optical activity is next. And again, we'll be doing that during the lab. Okay, Fischer projection. Spelled with a C there. You know, Fischer, involved in lots of things back in the 1800s. Assign RS to each compound. How do we do for this one? RS. RS. What'd you get?
I would say R because it's the lower priority group. It's in the back.
What's the low priority group? What is the low priority group on this carbon here? Chiral carbon.
Oh, the hydrogen.
Yeah, is it in the back or front?
No, it's in the plane.
It's in the plane. Plane. Okay? Yeah? Yeah, how would we do this? So did you get R or S?
I got
R? Okay, how do we do this? So we talked about if it's in the back, you just do it. If it's in the front, you do it and you reverse it, right? What about in the plane?
You just make sure that, I don't know.
Well, your book will tell you to do something. Okay? I'll tell you to do this. I would draw it in a Fischer projection. All right, let's look at it differently. Basically, we're going to draw this. You want to look at it with the H going back. Or front and reverse it, but if you're going to look at it different from this, you might as well look at it with the H in the back. To look at it with the H in the back, do I need to be standing over here or over here? I'm over here. There's the chiral carbon. I'm over here. The H is coming towards me from the chiral carbon. If I'm over here, the H is going away from me compared to the chiral carbon. I want to be over here with the H going away. Okay? I want to stand over here and look at it. What do I see? We can draw that. All right? Molecule. Very good. Carbon black straight up, H gray going away. Here it is. Chlorine green coming out towards you. Fluorine red going behind the board. Is that good? Okay. If I'm over here, the H, which I'm holding, is going away from me. Let's label these just so we know what they are. Here are the 3 right here. You see them? What's a high priority? Chlorine, fluorine, Okay? I'll draw it like that. You want to make it a round dial. 1, 2, 3. RS. 1 here, 2 here, 3 here. 1, 2, 3. What is it?
Clockwise.
R, red, black? I'm sorry. It's R. It's green, red, black. What is it? Yeah, it's R. Now, just by happenstance, the 1, 2, 3 here on the board looks clockwise as well. That's just flip. That's just luck. It has nothing to do with why we got R. It's because what I see. Does everybody see what I see here? Or would you like me to turn it? I turned it. That's 1, 2, 3. So what is it? Clockwise with the low priority group in the back. Okay? All right. But it's really helpful to be able to draw it like that on the board. Turn the view. It's like that on the board right now. Can't we draw it like that so you can look at it better? That's what a Fischer projection does. Okay, Fischer projection uses a crosshair. Like that. When you see this, this means we got the carbon. The things at top and bottom are going away from you. The things on the sides are coming towards you. There's the carbon. All right. That is, whenever you see a crosshair like that, it implies that it's this. The things on the sides are coming towards you, like cat whiskers or a bow tie, or these are my arms trying to hug you, things on the side coming forward. You see that? These on the side, these are forward, and those are going back. Okay? This is how we can do a chiral carbon. It's called a Fischer projection. This is it. Now also, that's top and bottom. I'm going to do this like this to make that top and bottom. If we look at that, and I turn here to show you what I see here, see the black is top, but it's going back. The H is bottom, but it's going back. And the two things on the sides are coming towards you. It's like we draw up there. All right? What do I see? I'm standing over here. I'm going to not do this because I'm going to do it like on your paper here now. Here we go. What do I see? If I'm looking through there, right? Really, it's almost not like this. And really, I need to make the little guy sort of slanted a little bit and look through there. Okay, the methyl is going straight up. The H is coming down towards my feet, the ground. But they're both going away from this carbon. All right? The methyl is going up and away. The H is coming down and away. Chlorine is coming to my left or right. It's a little bit like what we did before with Newman projections. Chlorine is coming which way? If I'm over here, the chlorine is on my right, because it's coming out of the board towards you guys. I'm just drawing on the board what I see, okay? I see a chlorine coming towards you. If I'm looking at it like this, it's over here. And the F by default must be there. There's the compound in a Fischer projection. If I'm looking at it, these two groups are coming towards me. Correct? If I'm over here looking at it, aren't these two groups coming towards me compared to that carbon? Yeah. There's the compound in a Fischer projection.
Thank you.
First one. Now, the power of this is it's much easier to look at. Let's do this. High priority, 1, 2, 3, 4. Okay? How's the H, front or back? Back. It's a Fischer projection. Top and bottom are back. With the low priority group back, how is 1, 2, 3? Clockwise. So it's R. Low priority group back, clockwise is R, right? The power of the Fischer is it's so much easier to see and deal with. And so a long time ago, somebody by the name of Fischer said, no, let's draw these compounds like this instead. They're easier to work with. Easier to see things. Okay. How about the one on the right? First off, what do you recognize about the relationship of that one to this one? Yeah, they're mirror images. Are they the same or different? Because again, 2 paper clips could be mirror images. We then have to say, are they same or different? How do you know they're different? Because it has 1 chiral carbon. Anything with 1 chiral carbon is going to be chiral. Mirror image is going to be different. So you know that. Also, if you had these 2 models, they would not be superimposable. Here are the 2 models. Are they superimposable? Black and green will line up. Good to go. Red and gray don't. They are not superimposable. No matter how we turn them, they will never superimpose. Yeah, these are enantiomers. If that's R, what is this one? I bet you a steak dinner it's S, because their mirror images are, the mirror image of R is S. Can we prove that? Can we draw this in a Fischer projection? And practice that and then prove it. Okay, which side do you want to stand on? H going away. So how about if we stand over here, look through there, and now I have methyl at top, H at bottom. Methyl at top, H at bottom. Correct? And if I'm over here with H going away, chlorine is on which side of? I see it on the left. Carbon, chlorine on the left. Correct? Okay. Carbon, chlorine on the left. That's a mirror image. F must be here. Look at the Fischers. Do the Fischers look like mirror images?
Yes.
Yes, they are. Okay. 1, 2, 3. H is in the front or back? H is low priority group here. 1, 2, 3. What is this? S. I told you. You owe me a steak dinner. Okay? It's S. This is Fischer projections. Crosshair, implied. Compounds with more than 1 chiral carbon. How many stereoisomers are possible for the following compound? Before we do that, how many stereoisomers are possible for this compound? How many stereoisomers possible? Well, when I say that, I love it when a student says, do you mean this, or can you clarify your question? I can see some clarification. How many total stereoisomers possible for said compound? How many total stereoisomers possible? 2. Yeah, they're on the board. One's R and one's S. 2 stereoisomers, yeah. Okay. How many stereoisomers are possible for the following compound? Somebody got it? Okay. Let's see what we can do here. How many chiral carbons here? Is that chiral? Yes. This one? Yes, both chiral. 2 chiral carbons. Number of stereoisomers equals 2 to the n. This is maximum number, though. Maximum number of stereoisomers. The reason it's called max is because sometimes there may be less than this number we're going to come up with. but there never will be more. We have to understand and identify when will there be less than this. The maximum number is to the n, where n is what? Number of what? It's bigger than that. That's that more broader definition. Number of stereogenic sites. A chirocarbon is an example of a stereogenic site. What is a stereogenic site? It's a site where you have stereochemistry. That is, it's a site where the way things are configured there, the way the molecule is built there, that has led to stereochemistry. Has the way that that carbon exists led to any stereochemistry up there? Yeah, it leads to two different configurations, R and S. What if the fluorine was a chlorine? You had two chlorines there. Would the way that molecule has been built lead to stereochemistry? No, you wouldn't have any stereochemistry. There's nothing there. A chirocarbon is a stereogenic site. What other types of sites have we seen? Alkenes are stereogenic sites. Because an alkene can be potentially cis or trans. It can potentially have stereochemistry. But not all alkenes. Only one of those alkenes on the quiz was stereogenic. How many stereogenic sites here? 2 chirocarbons. 2 to the n is what? 4. Yeah. 4 is the max. Should it be less than 4? We're going to have to figure that out. Okay. Think about drawing Fischer projections here. All right? We didn't do one today, but we'll certainly be doing all this on Friday. There's also questions ahead, guys.
That makes no sense. Slight little mystery.